Hello there, and welcome to the Sleepy Library. I'm so glad you found your way here tonight. Perhaps you've had a long day, or maybe you're simply someone who enjoys closing their eyes to the gentle rhythm of fascinating mysteries rather than counting sheep. Either way, you've arrived at exactly the right place. Tonight, we're embarking on a journey through some of the most intriguing, unexplained phenomena our universe has to offer. These aren't tales of fantasy, but genuine mysteries that continue to puzzle scientists, challenge our understanding, and remind us that despite all we've learned, the cosmos still holds countless secrets. Some of what you hear tonight may surprise you. Some may comfort you with the knowledge that wonder still exists in our world. And some may simply carry you gently into sleep. Before we begin, if these calm explorations help you unwind or give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let your breathing slow, your muscles relax, and your mind settle into a state of gentle curiosity. Let's begin. The universe is made mostly of things we cannot see. When you look up at the night sky, filled with stars and galaxies glowing across impossible distances, you might think you're seeing most of what exists. But the visible universe, everything that shines with light, makes up only about 5% of all that is. The remaining 95% consists of two mysterious substances that scientists can detect but cannot yet fully explain. Dark matter accounts for roughly 27%, while dark energy comprises about 68%. These are not mere gaps in our knowledge, but fundamental components of reality itself, invisible architects shaping the structure of everything we can see. Dark matter doesn't emit, absorb, or reflect light in any way. It passes through ordinary matter as though nothing is there. Yet, its gravitational effects are unmistakable and profound. Without dark matter, galaxies would fly apart. The stars within them spin too fast for visible matter alone to hold them together. Something unseen must be providing additional gravitational pull, binding these cosmic islands in ways that visible matter cannot explain. Scientists discovered this in the 20th century when they measured how galaxies rotate. The outer edges of spiral galaxies move at roughly the same speed as regions closer to the center, defying the expectations of Newtonian physics. If only visible matter existed, the outer stars should move more slowly, like planets in our solar system, where distant worlds orbit more leisurely than inner ones. The fact that galaxy rotation doesn't follow this pattern suggests an enormous halo of invisible matter surrounds each galaxy, extending far beyond the visible disk. Dark matter reveals itself through gravitational lensing, a phenomenon predicted by Einstein's general relativity. When light from distant galaxies passes near massive objects, the gravity of those objects bends the light's path, creating distorted or multiple images of the background galaxy. By studying these distortions, astronomers can map where dark matter exists, even though they cannot see it directly. The pattern of lensing matches what would be expected if vast quantities of invisible matter thread through the cosmos like an unseen web. One of the most compelling pieces of evidence comes from the Bullet Cluster, a region where two galaxy clusters collided billions of years ago. When the collision occurred, the hot gas from each cluster interacted and slowed down, glowing brightly in X-rays. But observations using gravitational lensing showed that most of the mass in the system didn't slow down at all. It passed straight through, separated from the gas, distributed in a pattern that reveals the presence of dark matter. The collision essentially pulled apart the visible and invisible components, offering a rare glimpse of dark matter's independent existence. Scientists have proposed several candidates for what dark matter might be. One leading theory suggests it consists of weakly interacting massive particles, or WIMPs, which would have significant mass but interact with ordinary matter only through gravity and possibly the weak nuclear force. Despite extensive searches using sensitive detectors deep underground, shielded from cosmic rays and other interference, no WIMP has been conclusively detected. Another candidate is the axion, a hypothetical particle with incredibly low mass, perhaps 10 trillionth the mass of an electron. Axions would be produced in vast numbers throughout the universe, and in the presence of strong magnetic fields, they might convert into detectable photons. Experiments designed to search for axions are ongoing, using powerful magnets and sensitive instruments to look for these elusive particles. Some scientists have wondered whether dark matter could be explained by modifying our understanding of gravity itself, rather than invoking new particles. These modified theories of gravity, known collectively as MOND theories, attempt to explain galactic rotation and other phenomena by altering the laws of gravity at large scales. However, these theories struggle to account for all the observational evidence, particularly the detailed patterns seen in gravitational lensing and the cosmic microwave background radiation. The weight of evidence suggests dark matter is indeed a real substance, even if its exact nature remains unknown. Dark matter doesn't just hold galaxies together, it plays a crucial role in cosmic structure formation. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny fluctuations in density. Dark matter, being unaffected by radiation pressure, could begin clumping together immediately. Its gravitational pull then attracted ordinary matter gathered in these dark matter halos, eventually forming the first stars and galaxies. Without dark matter as gravitational scaffolding, the universe would look entirely different, perhaps too smooth and diffuse to allow galaxies or stars to form at all. The distribution of dark matter throughout the universe follows a pattern often called the cosmic web. Filaments of dark matter stretch across vast distances, with galaxies forming along these threads like beads on a string. Where filaments intersect, massive clusters of galaxies gather, pulled together by the combined gravity of dark matter and ordinary matter. The largest structures in the universe, superclusters spanning hundreds of millions of light years, owe their existence to this underlying dark matter framework. It's humbling to realize that the glowing galaxies we can photograph represent only the visible peaks of much larger, invisible mountains of dark matter. Scientists estimate that in our own Milky Way galaxy, dark matter outweighs visible matter by a factor of about 6 to 1. A vast halo of dark matter surrounds the galactic disk, extending far beyond the furthest visible stars. This halo helps keep the galaxy stable, preventing it from tearing itself apart as it rotates. Dark matter particles may be passing through your body right now, billions of them every second, completely undetected and undetectable by ordinary means. They interact so weakly with normal matter that they slip through atoms as though the atoms weren't there. This property makes dark matter extraordinarily difficult to study directly. Experiments to detect dark matter particles typically operate deep underground, in mines or laboratories, where thick layers of rock shield the detectors from cosmic rays and other background radiation. These experiments look for the rare occasions when a dark matter particle might collide with an atomic nucleus in the detector, producing a tiny flash of light or a small amount of heat. Despite years of operation and increasingly sensitive instruments, these direct detection experiments have yet to produce a confirmed signal. The search continues, driven by the knowledge that discovering dark matter's true nature would revolutionize our understanding of physics. Some researchers have suggested that dark matter might not be made of particles at all, but could consist of primordial black holes, tiny black holes formed in the intense conditions of the early universe. These black holes would be far too small to swallow planets or stars, but their combined mass could account for dark matter's gravitational effects. However, observations place strict limits on how many such black holes could exist, and most evidence still points toward a particle-based explanation. The mystery deepens when we consider dark energy, the even more enigmatic component that makes up the majority of the universe. While dark matter pulls things together through gravity, dark energy does the opposite, seems to push space itself apart, causing the expansion of the universe to accelerate. This discovery, made in the late 1990s by two independent teams studying distant supernovae, came as a complete shock to scientists. Before these observations, physicists assumed that the expansion of the universe, which began with the Big Bang, would be gradually slowing down due to the gravitational attraction of all the matter in the cosmos. Instead, they found that the expansion was speeding up, as if some unknown force was overwhelming gravity on the largest scales. To visualize this, imagine throwing a ball into the air. You expect it to slow down, stop, and fall back to the ground pulled by gravity. But what if, instead of falling, the ball suddenly accelerated upward, moving faster and faster into the sky? This is essentially what's happening to the universe. Galaxies that are already moving apart are moving apart ever more quickly, driven by something that permeates all of space. Scientists call this mysterious influence dark energy, though the name merely labels our ignorance. We have no plausible explanation for what dark energy actually is. One possibility is that dark energy is a property of space itself. According to quantum field theory, even empty space isn't truly empty, but seethes with quantum fluctuations, virtual particles popping in and out of existence on timescales too brief to measure directly. These fluctuations might create a kind of energy inherent to the vacuum, an energy that doesn't dilute as space expands, but maintains constant density. If this vacuum energy has a repulsive gravitational effect, it could explain dark energy. This idea connects to something called the cosmological constant, a term that Albert Einstein originally added to his equations of general relativity. Einstein introduced the cosmological constant to make his equations compatible with a static universe, which was the prevailing belief at the time. When astronomical observations later revealed that the universe was expanding, Einstein abandoned the constant, reportedly calling it his biggest blunder. Ironically, the discovery of dark energy suggests that Einstein's cosmological constant might have been correct after all, though for different reasons than he imagined. The constant wouldn't keep the universe static, but would cause its expansion to accelerate, which is precisely what we observe. Another theory proposes that dark energy is a fifth fundamental force of nature, sometimes called quintessence. Unlike the cosmological constant, which would have the same strength everywhere and at all times, quintessence would be a dynamic field that could vary in strength from place to place or change over cosmic time. This field would fill the universe like a fluid, exerting negative pressure that pushes space apart. Different models of quintessence make different predictions about how dark energy's strength might evolve as the universe ages. Some scientists have suggested that the effects attributed to dark energy might indicate that our theory of gravity needs modification on the largest scales. Just as Einstein's general relativity modified Newton's laws of gravity, a new theory might be needed to describe gravity across billions of light years. Such theories are difficult to construct because they must explain not only cosmic acceleration, but also match all the other successes of general relativity, from the orbits of planets to the bending of light near massive objects. So far, no alternative theory of gravity has successfully explained all the observations as well as the dark energy hypothesis does. The accelerated expansion of the universe has profound implications for cosmic destiny. If dark energy continues to dominate, and its strength remains constant or grows stronger, the universe will keep expanding faster and faster. Eventually, this acceleration could tear apart galaxy clusters, then galaxies themselves, then solar systems, planets, and finally even atoms, in a scenario sometimes called the Big Rip. Alternatively, if dark energy's strength decreases over time, the expansion might slow, and the universe could eventually collapse back on itself in a big crunch. Or the expansion might continue forever, but at a gradually decreasing rate, leading to a cold, dark, eternally expanding cosmos where stars burn out and galaxies fade into isolated islands of darkness. Current observations suggest the expansion will continue indefinitely, though we cannot be certain how dark energy will behave in the distant future. We live in a special time in cosmic history, a period when dark energy has recently become dominant, but hasn't yet driven everything too far apart. For most of the universe's history, matter and radiation dominated, and gravity was winning the cosmic tug-of-war. The expansion was slowing down. Then, about 5 billion years ago, something changed. The universe had expanded enough that matter became sufficiently diluted, while dark energy, which doesn't dilute with expansion, began to take control. Since then, the acceleration has been building. If dark energy had dominated too early, matter wouldn't have been able to clump together to form galaxies and stars. We exist because dark energy waited, cosmologically speaking, allowing structure to form before taking over. The fact that we live just when dark energy becomes dominant has puzzled some scientists. Is this timing a coincidence, or does it tell us something deep about the relationship between dark energy and the emergence of complexity in the universe? Mapping dark energy requires measuring how the universe's expansion has changed over billions of years. Scientists do this by studying distant supernovae, extremely bright stellar explosions that can be seen across cosmic distances. A particular type, called Type 1a supernovae, explode with remarkably consistent brightness, making them useful as cosmic distance markers. By measuring how bright these supernovae appear, and comparing that to how bright they should be based on their distance, astronomers can determine how fast the universe was expanding at different times in the past. These measurements revealed the acceleration and continue to refine our understanding of dark energy's properties. Another method involves studying the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This radiation carries an imprint of conditions in the early universe, including tiny fluctuations in temperature that correspond to regions of slightly higher or lower density. By analyzing these patterns in exquisite detail, scientists can infer the composition of the universe, including how much dark energy it contains. Multiple independent measurements using different techniques all point to the same conclusion. Dark energy makes up roughly 68% of everything in the universe. Despite this agreement on how much dark energy exists, its fundamental nature remains one of the deepest mysteries in all of science. Understanding dark energy would not only explain why the universe is accelerating, but would also shed light on the nature of space, time, and the quantum vacuum. It might reveal new forces or particles, or require a complete revision of our understanding of gravity. The fact that 70% of the universe consists of something we don't understand is both humbling and exciting. It means that even with all our scientific progress, we've only begun to comprehend the full picture of reality. Some researchers have proposed that what we perceive as dark matter and dark energy might be manifestations of extra dimensions beyond the three spatial dimensions we experience. In these theories, gravity might be able to leak into other dimensions, affecting how it behaves on large scales and producing effects we attribute to dark matter and dark energy. While these ideas are mathematically intriguing, they remain speculative, lacking direct observational support. The search for understanding these invisible components of the universe continues to drive some of the most ambitious scientific projects ever undertaken. Massive telescopes scan the skies, mapping billions of galaxies to trace the distribution of dark matter through gravitational lensing. Underground detectors wait patiently for dark matter particles that might never arrive. Satellites measure the cosmic microwave background with unprecedented precision. Supercomputers run simulations of cosmic structure formation, comparing the predictions of different dark matter and dark energy models with observations. Each piece of data narrows the possibilities, gradually constraining what these mysterious substances could be. Yet even with all this effort, dark matter and dark energy keep most of their secrets. They are the invisible ocean in which visible matter floats, the hidden stage on which the cosmic drama unfolds. Every atom in your body, every photon of light, every star in the sky represents a tiny fraction of what exists. The rest is darkness, not the absence of things, but the presence of things beyond our current ability to perceive or comprehend. It's a reminder that the universe is stranger and more mysterious than we ever imagined. The very fabric of reality contains components that remain, for now, beyond our reach. Invisible players in a cosmic story we're only beginning to understand. Ball lightning appears without warning and defies explanation. Imagine a glowing sphere of light, roughly the size of a grapefruit, floating through the air during a thunderstorm. It moves independently of the wind, sometimes passing through closed windows without damaging them, other times exploding with a loud bang. It can last for seconds or even minutes, far longer than an ordinary lightning flash. This phenomenon is called ball lightning, and despite centuries of reports, it remains one of nature's most perplexing mysteries. Witnesses have described ball lightning throughout recorded history. Descriptions appear in medieval manuscripts, ship logs from the age of exploration, and modern scientific journals. The reports share common features across cultures and centuries. The spheres typically range from a few centimeters to about a meter in diameter, though sizes outside this range have been reported. They glow in various colors, most commonly yellow, orange, white, or blue, sometimes shifting between hues. They often make a hissing or buzzing sound and emit a distinctive acrid smell, possibly ozone or sulfur. They move erratically, sometimes bouncing off surfaces, sometimes gliding smoothly through the air, and occasionally remaining stationary. Ball lightning appears most often during thunderstorms, suggesting a connection to conventional lightning, but the exact relationship remains unclear. One particularly well-documented historical account comes from the 18th century, when ball lightning allegedly appeared during a church service in England, killing several people and causing structural damage. More recent reports come from airplane pilots, submarine crews, and ordinary people in their homes. In 2014, Chinese scientists captured what may be the first verified footage of ball lightning during a thunderstorm, along with spectrographic data showing the presence of silicon, iron, and calcium. This observation lends support to one of the leading theories about ball lightning's origin. The silicon hypothesis, proposed by scientists in New Zealand, suggests that when ordinary lightning strikes the ground, it can vaporize silicon from soil and separate it from oxygen. The pure silicon vapor, still hot and reactive, might then condense into a network of nanoparticles that gradually recombine with oxygen from the air. This recombination releases energy in the form of light and heat, creating a glowing sphere that persists until the chemical fuel is exhausted. Laboratory experiments have successfully created ball lightning-like phenomena using this method, producing luminous orbs that lasted several seconds. However, these artificial creations don't perfectly match all reported characteristics of natural ball lightning, leaving questions about whether silicon chemistry fully explains the phenomenon. Another theory proposes that ball lightning consists of a special type of plasma, a state of matter where gas becomes ionized, with atoms losing electrons and becoming electrically charged. Ordinary lightning creates plasma, but it exists for only fractions of a second before dissipating. For ball lightning to be plasma, some mechanism must stabilize it for much longer periods. Various proposals exist for how this stabilization might occur. Some suggest that the plasma ball traps its own magnetic field, which helps contain it. Others propose that the ball is actually a vortex ring of plasma, like a smoke ring made of ionized gas, with the ring structure providing stability. Still others suggest that microwave radiation from the lightning strike might be trapped inside a plasma bubble, continually re-energizing it. Each of these ideas has strengths and weaknesses, and none has been conclusively proven or disproven. A more recent theory suggests that ball lightning might be an optical phenomenon rather than a physical object. According to this idea, intense light from a lightning strike could become trapped in a thin shell of compressed air with unusual optical properties. The light would circulate inside this shell, bouncing off the inner surface through total internal reflection, similar to how light travels through fiber optic cables. The circulating light would compress the air further through a process called electrostriction, where light pressure squeezes the material it passes through. This creates a self-sustaining bubble of light, glowing brightly from the intense circulating radiation, while remaining stable for seconds or minutes. The optical theory explains several puzzling aspects of ball lightning behavior, including why it seems to pass through windows without breaking them. If ball lightning is essentially trapped light rather than a solid or plasma object, it could theoretically interact with glass in ways that conventional matter cannot. The theory also explains why ball lightning tends to float or move horizontally rather than rising like a hot air balloon, as heated plasma should. Optical forces, which depend on the intensity and distribution of light within the sphere, could counteract buoyancy and even propel the sphere in unexpected directions. However, the optical theory requires extremely high light intensities, about 1 billion times greater than sunlight, which seems difficult to achieve and maintain in a natural setting. Critics question whether such intense light could be generated and trapped long enough to match eyewitness accounts. Despite these various theories, single explanation accounts for all reported ball lightning characteristics. Some observations seem to support the silicon hypothesis, while others fit better with plasma or optical models. It's possible that ball lightning isn't a single phenomenon, but several different effects that produce similar visible results. Different atmospheric conditions, soil compositions, or lightning properties might create different types of glowing spheres, all grouped under the umbrella term of ball lightning. The unpredictability and rarity of ball lightning make it extraordinarily difficult to study. Unlike regular lightning, which scientists can trigger using rockets trailing wires into thunderclouds, ball lightning has never been reliably produced on demand in natural conditions. Laboratory experiments can create ball lightning-like effects, but whether these match natural ball lightning remains uncertain. The phenomenon simply doesn't occur often enough or predictably enough to allow systematic observation with scientific instruments. Even with the proliferation of cameras in modern times, clear footage of ball lightning remains rare. Many purported videos turn out to show other phenomena, artifacts of the camera lens, or effects that cannot be verified as genuine ball lightning. The 2014 Chinese observation stands out precisely because it was captured by scientific instruments during an ongoing research project studying ordinary lightning. That serendipitous recording provided valuable data, but also highlighted how rare such opportunities are. Some skeptics have argued that ball lightning might not be a physical phenomenon at all, but rather a perceptual effect or hallucination. One study suggested that the intense magnetic fields produced by nearby lightning strikes could stimulate the retina or visual cortex, creating the illusion of seeing a glowing sphere. According to this idea, what witnesses perceive as ball lightning external to themselves is actually a phosphene, a visual sensation produced directly in the eye or brain. This would explain why ball lightning seems to behave in physically implausible ways, why multiple witnesses sometimes report seeing it in different locations simultaneously, and why it leaves limited physical evidence. However, there are reports of ball lightning causing damage, leaving burns, or producing lasting effects, which suggests at least some events involve real physical objects. The debate over ball lightning's reality and nature continues. Most scientists now accept that at least some ball lightning reports describe genuine physical phenomena, but consensus on what causes it remains elusive. The phenomenon sits at an uncomfortable intersection of atmospheric physics, plasma science, chemistry, and electromagnetism, requiring expertise across multiple disciplines to fully understand. It also suffers from a lack of reproducible observations, the gold standard of scientific investigation. Without the ability to create and study ball lightning under controlled conditions, researchers must rely on eyewitness accounts, chance observations, and theoretical models. This makes progress slow and uncertain. Meanwhile, ball lightning continues to appear, glowing briefly before vanishing, leaving behind more questions than answers. It serves as a reminder that even in the age of advanced technology and scientific understanding, nature still produces surprises we cannot fully explain. The next time a thunderstorm rolls through, somewhere in the world, someone might look out their window and see a glowing sphere floating impossibly in the air. A visitor from the frontier of our knowledge, where observation meets mystery and the boundaries of the explainable blur into the unknown. For now, ball lightning remains what it has always been, a rare and beautiful enigma, witnessed by thousands but understood by none. The Taos hum has puzzled residents and visitors for decades. In the small town of Taos, New Mexico, nestled in the high desert at the base of the Sangre de Cristo Mountains, some people hear a sound that others cannot detect. They describe it as a persistent, low-frequency hum, like the distant rumble of a diesel engine idling, or the throb of heavy machinery operating somewhere just out of sight. It's always there, day and night, never stopping, never varying in pitch or rhythm. But no source has ever been found. Scientists, engineers, and government investigators have searched for explanations, yet the origin of the Taos hum remains unknown. The phenomenon first gained widespread attention in the early 1990s, when local residents began reporting the mysterious hum to authorities. Not everyone could hear it, which made the situation even more perplexing. Studies suggested that only about 2% of the population in the Taos area could perceive the sound. Those who did hear it found it deeply disturbing. Many reported difficulty sleeping, increased stress, headaches, and a general sense of unease. The hum seemed louder indoors than outdoors, and stronger at night than during the day. Some sensitive individuals could hear it throughout the surrounding region, while others only noticed it in specific locations or buildings. This selectivity added to the mystery. If the hum came from a fixed external source, why would some people hear it while their neighbors did not? And why would it seem louder inside buildings, where walls should provide some sound insulation? Investigators from various organizations attempted to identify the source. Teams with acoustic monitoring equipment searched for unusual sounds in the area. They looked for industrial facilities, military installations, power lines, and underground tunnels that might produce low-frequency vibrations. They measured seismic activity, electromagnetic fields, and atmospheric pressure variations. Despite these efforts, no definitive source was found that could account for the hum. Reports. Some measurements detected weak, low-frequency sounds in the area, but nothing strong enough or consistent enough to explain what the affected residents described. Moreover, similar low-frequency sounds exist in many places without anyone reporting a disturbing hum. Several hypotheses have been proposed to explain the Taos hum. One early theory suggested it came from radio frequency radiation, possibly from military communication systems, affecting the auditory nerves of sensitive individuals. However, this theory fell out of favor when careful measurements found no unusual electromagnetic fields in the area. Another hypothesis pointed to ultra-low-frequency seismic waves propagating through the Earth's crust, perhaps generated by natural processes or human activity elsewhere, and transmitted through rock to emerge in the Taos region. While the Earth does carry such waves constantly, no correlation was found between seismic measurements and residents' experiences of the hum. A more recent theory suggests the sound might originate from distant industrial or natural sources and be amplified or channeled by the local geography or atmospheric conditions. The mountains surrounding Taos could potentially focus sound waves the way a parabolic dish focuses light, concentrating distant noises into the valley where the town sits. However, this doesn't explain why only a small percentage of residents hear it, or why it seems to occur worldwide in disparate locations. Taos is not unique. Reports of mysterious hums have come from numerous places around the world, from Windsor in Ontario, Canada, to Bristol in England, to Auckland in New Zealand. These locations share few obvious similarities in geography, climate, or human activity. Yet the descriptions of the hum are remarkably consistent across different sites. The affected individuals typically describe a low-pitched, rumbling or throbbing sound between 40 and 80 Hz, at the lower limit of human hearing. They often cannot determine where it's coming from or point in its direction. They report that it interferes with sleep and quality of life, and most notably, only a small minority of the local population can hear it, while the majority notice nothing unusual. This consistent pattern across diverse locations suggests a common underlying cause, but that cause remains elusive. Some researchers have proposed that the hum might not have an external source at all. Instead, it could be a form of tinnitus, a condition where people hear sounds that have no external origin. Tinnitus typically manifests as ringing in the ears, but it can also produce humming, buzzing, or roaring sounds. However, the Taos hum differs from typical tinnitus in important ways. People with tinnitus usually hear it everywhere they go, while hum hearers often report that the sound disappears when they travel outside the affected area. Additionally, tinnitus is usually subjective, varying between individuals, while hum descriptions show striking consistency within each affected region. Another neurological explanation suggests that some people's auditory systems might be unusually sensitive to very low-frequency sounds or vibrations that most people cannot consciously perceive. The human ear can detect sounds down to about 20 Hz, but below that frequency, sounds transition into vibrations that we feel rather than hear. Some individuals might have auditory systems that extend slightly lower into this infrared region, allowing them to hear what others only feel or don't notice at all. This heightened sensitivity could make them aware of low-frequency environmental sounds, perhaps from industrial equipment, traffic, or natural sources, that fall below the threshold for most people. However, this theory doesn't explain why the sensitivity would be geographically clustered in specific towns rather than randomly distributed throughout the population. Industrial and mechanical sources remain suspects despite the lack of clear evidence. Modern society produces countless sources of low-frequency sound and vibration. Power plants, cooling systems, ventilation fans, traffic, trains, and various industrial processes all generate noise in the low-frequency range. These sounds can travel long distances and penetrate buildings more easily than higher frequencies. In some cases, documented hums have been traced to specific industrial sources. In the town of Kokomo, Indiana, reports of a mysterious hum were eventually linked to cooling tower fans at a local manufacturing plant. When the fans were modified, the reports decreased significantly. This success story showed that mysterious hums can sometimes be solved, but it also highlighted how difficult the detective work can be. It took considerable effort and resources to identify the Kokomo source, and not all hum reports have been similarly resolved. In many locations, including Taos, no such obvious industrial source exists, or if it does, it has successfully hidden from investigators. Some speculation has focused on military activity, particularly extremely low-frequency communication systems used to communicate with submarines deep underwater. These systems operate in the range of 3 to 30 Hz, well below the threshold of normal hearing, but potentially detectable by sensitive individuals as vibrations. However, the global shutdown of several ELF transmitters in recent decades hasn't corresponded with a decrease in hum reports, casting doubt on this explanation. Natural sources have also been considered. The Earth itself produces low-frequency sounds through various mechanisms. Ocean waves hitting coastlines create microseisms, subtle vibrations that travel through the planet. Atmospheric pressure waves, aurora, and even meteors entering the atmosphere can generate infrasonic sounds. Could some combination of natural phenomena be responsible for the hum? This seems unlikely, given that natural sounds of this type have always existed, while hum reports appear to be a relatively modern phenomenon, mostly emerging in the late 20th century. Of course, this could reflect increased awareness and reporting, rather than a genuinely new phenomenon. Perhaps people have always heard these sounds, but only recently began discussing them openly and seeking explanations. The psychological dimension of the hum cannot be ignored. Living with an unexplained, persistent sound can be profoundly stressful. Some researchers have suggested that once people become aware of the hum and convinced that something unusual is occurring, they may become hyper-attentive to background sounds that they would normally filter out unconsciously. This hypervigilance could amplify the perceived loudness and persistence of the hum, creating a feedback loop where paying attention to the sound makes it seem more intrusive, which leads to paying even more attention. However, this psychological component doesn't necessarily mean the hum isn't real. It's possible both that a genuine environmental sound exists and that psychological factors influence how severely it affects different individuals. The Taos hum remains unsolved. The phenomenon continues to affect some residents, while remaining undetectable to most people and to scientific instruments. This peculiar selectivity makes it one of the most frustrating mysteries in modern acoustics. Sound is, fundamentally, vibration traveling through a medium. We have excellent tools for measuring vibrations, yet these tools have not revealed the source of the Taos hum, leaving researchers, residents, and skeptics equally puzzled. For those who hear it, the hum is an undeniable presence, a constant companion that intrudes on quiet moments and disturbs rest. For those who don't hear it, the hum might as well not exist, an invisible phantom that belongs more to folklore than to physics. The divide between hearers and non-hearers creates a strange social boundary, where lived experience cannot be shared or validated through common perception. It's an isolating experience to sense something that others cannot confirm, to know with absolute certainty that a sound fills the air while the person standing next to you insists on silence. This isolation is perhaps the most troubling aspect of the phenomenon, beyond any physical discomfort the sound itself creates. The mystery of the Taos hum reminds us that perception itself can be unexplained. We like to think that reality is objective, that if something exists, everyone should be able to detect it with the right instruments. But the boundary between sensation and environment is more complex than that simple view suggests. Sounds at the edge of human perception, where physics meets neurology, can create experiences that are both entirely real to the individual and entirely undetectable to others. Until the day when someone definitively identifies the source of the hum, or proves conclusively that no external source exists, the phenomenon will continue to occupy that uncomfortable space between the physical and the perceptual, between the measurable and the experienced. A quiet, droning reminder that our understanding of even something as fundamental as sound remains incomplete. Consciousness arises from matter, but cannot be reduced to it. Every moment of your existence is filled with subjective experience. You see colors, hear sounds, feel emotions, and maintain a continuous sense of being yourself. This stream of conscious awareness seems like the most obvious fact about reality, yet it presents one of the deepest puzzles in all of science. How does consciousness arise from physical matter? How do electrochemical signals in neurons create the felt quality of experience? Why does the universe contain subjects, beings who experience rather than just react? These questions form what philosophers call the hard problem of consciousness. And despite enormous advances in neuroscience, they remain stubbornly unanswered. The easy problems of consciousness, in contrast, involve understanding the mechanisms of brain function. How do we process visual information? What neural circuits enable language? How does memory work? These questions are challenging and far from fully solved, but they're easy, in the sense that we can imagine how they might be explained in terms of physical processes. We can trace how light hitting the retina triggers signals that travel through the visual cortex, how different neurons respond to edges, colors, and movements, how these signals combine to create internal representations of the external world. But this entire chain of physical causation doesn't explain why there is something it's like to see red, why the experience of redness has a particular quality that distinguishes it from seeing blue or hearing a tone. The philosopher Thomas Nagel captured this puzzle in a famous essay asking what it's like to be a bat. Bats navigate using echolocation, emitting ultrasonic squeaks and interpreting the returning echoes to build a picture of their surroundings. We can study the bat's brain, measure the neural activity, and understand the information processing involved. But we cannot know what echolocation feels like from the inside. There is presumably something it's like to be a bat, but that subjective experience is unavailable to us, and cannot be deduced from objective third-person descriptions of the bat's neural activity. The same applies to human consciousness. No amount of information about brain states seems to capture what it's actually like to experience those states. If you'd never experienced the color red, and someone described to you every physical fact about how the brain processes red light, you still wouldn't know what red looks like. There's an explanatory gap between the physical description and the subjective experience. Some philosophers argue this gap is unbridgeable in principle, that consciousness is fundamentally different from physical processes and cannot be explained by them. Others suggest the gap reflects limitations in our current understanding, and that future neuroscience might close it. But so far, no theory successfully bridges the divide. Neuroscientists have made remarkable progress in identifying neural correlates of consciousness, specific brain states and activities that consistently accompany conscious experiences. When you consciously see an object, certain patterns of neural firing occur in your visual cortex and other brain regions. When you're unconscious, under anesthesia, or in deep sleep, those patterns disappear. By comparing brain activity during conscious and unconscious states, researchers can identify which neural processes seem necessary for consciousness to exist. These correlates help us understand where in the brain consciousness arises and what kinds of neural activity accompany it. But they don't explain why those neural processes produce subjective experience rather than operating unconsciously like a computer. One influential theory, the integrated information theory, proposes that consciousness corresponds to integrated information in a system. According to this view, consciousness arises when information is both differentiated and unified. A brain is conscious because it contains many specialized regions processing different types of information, and these regions are highly interconnected, allowing the information to be integrated into a unified experience. The theory provides a mathematical framework for quantifying how much integrated information a system contains, called phi. Systems with high phi are more conscious than systems with low phi. This theory makes testable predictions and has generated interesting research, but critics argue it doesn't really solve the hard problem. Even if we accept that integrated information correlates with consciousness, why should integrated information feel like something? Why isn't it just complicated information processing without any accompanying experience? Another approach, global workspace theory, suggests that consciousness arises when information becomes globally available across the brain. According to this theory, much neural processing occurs unconsciously in specialized modules. Information becomes conscious when it's broadcast to a global workspace, a network of brain regions that can access and manipulate it. This broadcast enables flexible behavior, verbal reports, and deliberate control. Global workspace theory explains many aspects of consciousness, including why attention is necessary for conscious awareness, and why we can consciously access only a limited amount of information at any time. But again, critics point out that this theory explains the functions of consciousness, what it does, without explaining why those functions are accompanied by subjective experience. Couldn't a brain broadcast information globally without anyone being home to experience it? Some researchers have explored the possibility that consciousness is not unique to brains, but is a fundamental feature of the universe, present to some degree in all matter. This view, called panpsychism, suggests that even electrons and quarks possess rudimentary forms of experience. Complex consciousness like ours would then emerge when vast numbers of these microconscious elements combine in the right way. Panpsychism seems strange at first, but it has a certain logic. If consciousness appears nowhere in the fundamental building blocks of reality, How does it suddenly emerge in sufficiently complex arrangements? Perhaps it's easier to explain consciousness as present from the start, built into the fabric of nature at the most basic level, than to explain how it emerges from purely non-conscious ingredients. Critics of panpsychism argue that calling an electron conscious stretches the word beyond recognition and doesn't really explain human consciousness any more than conventional neuroscience does. Others point out that even if we grant some rudimentary awareness to fundamental particles, we still need to explain how these combine into unified conscious experiences like yours. Why do the micro-experiences in your brain combine into one consciousness rather than remaining scattered? This is known as the combination problem, and it's no easier than the hard problem itself. The question of consciousness connects to other deep puzzles. What is the self, the I that experiences? When you introspect, you find thoughts, sensations, and feelings, but no separate experiencer standing apart from the experiences themselves. Yet you undeniably have a sense of being a continuing subject, the same person from moment to moment and across years. Neuroscience and psychology have shown that this sense of self is constructed, not given. The brain constantly integrates information from multiple sources and across time to create the feeling of a unified, persisting agent. But if the self is constructed, what does the constructing? This question loops back on itself in dizzying ways, suggesting that our ordinary intuitions about consciousness and self may be deeply misleading. Some spiritual and philosophical traditions have long claimed that the self is an illusion, that what we take to be a solid, independent observer is really a flowing process, empty of inherent existence. Modern neuroscience seems to support this view in surprising ways, finding no neural seat of the self, no central location where you reside. Instead, selfhood emerges from the coordinated activity of many brain regions, none of which alone constitutes the self. This distributed, process-based picture challenges our intuitions, but might be closer to the truth than the common-sense notion of a unitary self looking out through your eyes. Free will presents another aspect of the consciousness mystery. Do you choose your actions freely, or are they determined by prior causes? When you make a decision, it feels like you're the source of the choice, the ultimate author of your action. But neuroscience experiments have shown that neural activity predicting your decision begins before you're consciously aware of having made the choice. This suggests that the brain has already committed to an action before the conscious mind knows about it. Does this mean free will is an illusion, or does it just show that consciousness lags slightly behind neural processing, receiving updates about decisions made unconsciously? The debate continues, with profound implications for moral responsibility, law, and our self-understanding. If our choices are predetermined by neural processes we don't control, what does that mean for concepts like guilt, praise, and personal accountability? Consciousness might have evolved for adaptive reasons. Being aware of your environment, able to model possible futures, simulate outcomes, and deliberate before acting provides obvious survival advantages. A conscious organism can respond flexibly to novel situations in ways that fixed instinctive behaviors cannot. This evolutionary perspective helps explain why consciousness exists, but again, it doesn't explain how. Even if we grant that natural selection favored conscious creatures, we still face the question of how neural activity produces subjective experience. Evolution tells us that consciousness was useful, not how it's possible. Some scientists and philosophers have suggested that we might never solve the hard problem because our brains are not capable of understanding themselves in the required way. Just as a dog cannot understand quantum mechanics, humans might lack the cognitive apparatus needed to grasp how neural activity becomes subjective experience. Our intuitions and concepts evolved for dealing with the physical world, not for understanding the relationship between matter and mind. This limitation might be fundamental, an insurmountable barrier built into the structure of our cognition. If this pessimistic view is correct, consciousness will remain forever mysterious, not because it's inherently mysterious, but because we're not smart enough to solve the puzzle. Others are more optimistic, believing that continued research in neuroscience, artificial intelligence, and philosophy will gradually illuminate the mystery. Perhaps we need a conceptual revolution, a new framework that transcends the current categories of physical and mental. Such revolutions have happened before in science. Quantum mechanics required abandoning intuitive notions of particles and waves. Relativity demanded rethinking space and time. Maybe understanding consciousness will require an equally radical reconceptualization, one we cannot yet imagine. Meanwhile, consciousness research continues, driven by both curiosity and practical concerns. Understanding consciousness could help treat disorders of consciousness like coma and vegetative states, improve anesthesia, and shed light on mental illnesses. It might guide the development of artificial intelligence, raising questions about whether machines could become conscious and how we'd know if they did. As AI systems grow more sophisticated, capable of conversation, creativity, and complex behavior, the question of machine consciousness becomes increasingly urgent. Would a sufficiently advanced AI have subjective experiences? Would it deserve moral consideration? These aren't just theoretical questions, but practical ones that society may need to confront within the coming decades. For now, consciousness remains what it has always been, the most intimate and immediate aspect of existence, the foundation of everything we know, and yet the most difficult to explain. You are conscious right now, aware of these words, perhaps feeling the weight of your body, hearing ambient sounds, having thoughts and reactions. This experience is undeniable. It's the one thing you cannot doubt, because even doubting requires consciousness. Yet how this inner light exists, how subjective awareness emerges from objective matter, remains as mysterious as ever. As you rest tonight, your consciousness will fade into sleep, that strange daily disappearance of awareness. But even in sleep, you are not fully unconscious. Dreams arise, experiences that feel real while they last, generated entirely within your brain without external input. And underlying sleep is the continuous activity of the sleeping brain, maintaining life, processing memories, preparing for tomorrow's waking. Consciousness ebbs and flows, sometimes bright and focused, sometimes dim and scattered, sometimes gone entirely. But what it is, in its essence, remains unknown. This mystery won't disturb your sleep. If anything, it might comfort you to know that even with all our scientific knowledge, some things remain beyond explanation. The fact of your own awareness, this simple, undeniable presence, is more certain than any scientific theory. You don't need to understand consciousness to have it. You don't need to solve the hard problem to dream. So let yourself sink into the mystery, into the strange and beautiful fact that matter can be aware of itself, that the universe contains subjects as well as objects, that tonight as you sleep, you carry within you one of the deepest puzzles existence has to offer. The Pioneer spacecraft are veering off course for unknown reasons. In the 1970s, humanity launched 4 spacecraft toward the outer solar system and beyond. Pioneer 10 and 11 flew past Jupiter and Saturn, sending back stunning images before heading out toward interstellar space. Voyager 1 and 2 followed similar paths, visiting multiple planets and still operating decades later. These missions were triumphs of engineering and exploration, extending our reach across the solar system. But decades after launch, scientists noticed something puzzling about the Pioneer spacecraft. They were not quite where they should be. The deviation was tiny, about 380,000 kilometers after traveling billions of kilometers, but it was real and persistent. The spacecraft were being slowed by a force no one could explain. This unexpected deceleration became known as the Pioneer anomaly, and it sparked years of investigation and speculation. The trajectory of a spacecraft is governed by gravity, and any forces applied through thruster firings. If you know where a spacecraft starts, how fast it's moving, and what gravitational influences it encounters along the way, you can predict its future position with extraordinary accuracy. The Pioneer spacecraft carried no fuel for course corrections in their outward journey, so their paths should have been determined purely by gravity. Mission controllers tracked the spacecraft using radio signals, measuring the Doppler shift in the signals to determine velocity and the time delay to determine distance. As the years passed, they accumulated precise data on the spacecraft's positions and motions. When analysts examined this data carefully, they found a small but consistent discrepancy. The Pioneer spacecraft was slowing down slightly more than gravity alone could explain. The anomalous acceleration amounted to about 8.7 times 10 to the minus 10 meters per second squared. That's an unimaginably small force, about 10 billion times weaker than Earth's gravity at the surface. Yet, it was persistent and measurable. Both Pioneer 10 and 11 showed the same effect, which argued against it being a random error. The acceleration pointed toward the Sun, suggesting it might be related to some property of the spacecraft themselves or some unknown interaction with the solar system. Scientists considered every possible explanation. Could the measurements be wrong? Careful reanalysis of the data confirmed the anomaly. Could the spacecraft be leaking propellant, creating thrust? Both spacecraft had exhausted their attitude control fuel years earlier. Could gravitational effects from the outer planets or the Sun's mass be miscalculated? The known mass distribution in the solar system was well understood and couldn't account for the discrepancy. Could there be a belt of dark matter in the outer solar system, exerting unexpected gravity? This seemed unlikely and would have other observable consequences that weren't seen. The Pioneer anomaly generated excitement because it hinted at new physics. Perhaps Newton's and Einstein's theories of gravity needed modification at very large distances. Such modifications had been proposed to explain other puzzles, like the rotation of galaxies without invoking dark matter. If gravity behaved slightly differently than expected on solar system scales, it might show up as an anomalous acceleration of distant spacecraft. This possibility was intriguing, but required extraordinary evidence. Modifying gravity is not something to be done lightly, given how well established these theories are. Other exotic explanations included unknown forces from the quantum vacuum, interactions with cosmic background radiation, or effects from extra dimensions. These ideas were speculative at best, lacking independent support, but the persistent anomaly demanded explanation. And if conventional physics couldn't provide one, perhaps unconventional physics would be necessary. The mystery persisted for years, a small but nagging discrepancy in an otherwise perfectly understood system. Then, in the 2000s, a new analysis provided a more prosaic explanation. Scientists examined in detail the heat generated by the spacecraft's radioactive power source. The Pioneer spacecraft used radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity. This process is inefficient. Most of the heat is radiated away into space. The key insight was that this thermal radiation is not perfectly symmetric. The spacecraft's design means more heat is radiated in certain directions than others. The slightly asymmetric emission of thermal photons could produce a tiny thrust, like a very weak rocket engine. When researchers carefully modeled the spacecraft's thermal emissions, taking into account the geometry of the spacecraft and the location of the heat source, they found that thermal radiation could account for almost exactly the observed anomalous acceleration. The calculation required detailed knowledge of the spacecraft's design and how the power output of the generator decreased over time as the plutonium decayed. When all these factors were included, the mystery evaporated. The Pioneer anomaly wasn't new physics after all, but rather a subtle engineering effect that hadn't been fully accounted for in the original mission planning. This resolution was both satisfying and disappointing. Satisfying because it showed that the laws of physics didn't need revision, that a careful application of known principles could explain the anomaly. Disappointing because it meant the Pioneer spacecraft weren't revealing new truths about the universe, but were behaving exactly as they should, given a complete understanding of their thermal properties. The Pioneer anomaly illustrates an important aspect of scientific mysteries. Sometimes, the most exotic explanations prove correct, forcing us to revise our understanding of nature. But more often, careful analysis revealed that the mystery arose from incomplete information or overlooked details. The Pioneer story also highlights the challenge of eliminating systematic errors in complex experiments. The thermal radiation explanation had been suggested earlier, but required painstaking analysis of the spacecraft's design and thermal history to verify. Only when researchers accessed the original engineering documents and recreated detailed thermal models could they confirm that thermal effects explained the anomaly. Despite this resolution, some questions linger. The Voyager spacecraft, which followed similar trajectories, do not show the same anomaly. This difference actually supports the thermal explanation, since Voyager spacecraft have different designs and different thermal characteristics than the Pioneers. However, the Voyager data is also noisier, making small effects harder to detect. As of now, there is no indication of unexplained forces acting on any spacecraft in the solar system, though scientists continue to monitor trajectories carefully. If a genuine anomaly appeared consistently across multiple spacecraft, it would be much harder to explain away and might indeed point toward new physics. The story of the Pioneer anomaly reminds us to be both open-minded and skeptical. When observations don't match predictions, it's worth considering radical explanations, but it's also worth double-checking the mundane ones. In this case, the boring explanation won, but the investigation was valuable nonetheless. It improved our understanding of spacecraft thermal dynamics, refined our models of solar system gravity, and demonstrated the importance of precise tracking for future missions. And it provided a cautionary tale about crying new physics too soon. The universe still holds genuine mysteries, phenomena that cannot be explained by current knowledge. But distinguishing between real mysteries and merely overlooked details requires patience, rigor, and a willingness to consider that sometimes the most mundane explanation is the correct one. As you drift towards sleep tonight, consider the layers of complexity hidden in even the simplest phenomena. A spacecraft traveling through empty space seems like it should be easy to understand, governed only by gravity and its own momentum. Yet even this straightforward scenario held surprises that took decades to unravel. If something as controlled and well-measured as a space mission can harbor puzzles, imagine the hidden complexities in the natural world around you, in the biological systems that keep you alive, in the neural processes that will soon carry you into sleep. The universe is intricate beyond measure, and our understanding, though vast, remains incomplete. That's not a failure, but an opportunity. Every answered question reveals new questions waiting beneath. Every mystery solved uncovers deeper mysteries. The pioneer anomaly is resolved, but countless other puzzles remain, waiting for curious minds to investigate them, waiting for the right insight or measurement or theory to illuminate what is now dark. For now, though, you need not worry about unanswered questions. Let them rest as you rest. Tomorrow, they'll still be there, patiently awaiting attention. Tonight, it's enough to know that the universe is both knowable and endlessly mysterious, that human ingenuity can solve puzzles given time and effort, and that even when we think we understand something completely, surprises may still await. The pioneers fly on, silent and distant, their mission complete, their mystery resolved, heading slowly out of the solar system into the vastness beyond, carrying with them a message from humanity to whoever or whatever might someday find them in the endless dark. Your mind holds healing powers beyond understanding. Consider a patient sitting in a doctor's office, receiving what they believe is a powerful new medication for their chronic pain. They take the pill faithfully, twice daily, and within weeks they feel significantly better. Their pain decreases, their mood improves, their quality of life transforms. Then they learn the truth. The pills contained no active ingredient, only inert substances like sugar or starch. They were taking a placebo. Yet the relief was real, the improvement measurable, the healing genuine. This is the placebo effect, and it reveals something profound about the relationship between mind and body, between expectation and physiology, between belief and biological reality. For centuries, placebos were dismissed as mere tricks, psychological illusions that produced no real change. But modern neuroscience has revealed that placebo effects are not imaginary. They involve measurable changes in brain chemistry, neural activity, and physiological processes. The brain, responding to context, expectation, and belief, can trigger healing mechanisms that produce genuine therapeutic benefits. Understanding how this works opens a window into one of the most fascinating intersections of psychology, neuroscience, and medicine. The placebo effect works through multiple interacting mechanisms. One key pathway involves expectation and learning. When you expect relief, your brain activates systems designed to provide that relief. In the case of pain, expecting pain reduction triggers the release of endogenous opioids, natural pain-killing chemicals produced by your own brain. These substances bind to the same receptors targeted by morphine and other opioid drugs, reducing pain signals and creating a sense of well-being. Brain imaging studies have confirmed this process. When people receive placebo pain treatments, scans show increased activity in brain regions involved in opioid production, particularly the prefrontal cortex and an area called the periaqueductal gray in the brainstem. These regions coordinate the brain's descending pain control system, a network that can modulate pain signals traveling up the spinal cord before they reach consciousness. In essence, the brain has its own pharmacy, capable of dispensing powerful medications when triggered by the right psychological conditions. Dopamine, another crucial neurotransmitter, also plays a role in placebo effects. Studies of Parkinson's disease patients receiving placebo treatments show increased dopamine release in the brain's basal ganglia, the the very regions affected by the disease. These patients experience genuine motor improvements, measurable reductions in tremors and rigidity, all from treatments with no pharmacological ailments. Activity. The expectation of benefit triggers dopamine release, which temporarily compensates for the dopamine deficiency that characterizes Parkinson's disease. This demonstrates that placebo effects aren't limited to subjective experiences like pain, but can influence objective physiological processes. The placebo effect also involves classical conditioning, a form of learning discovered by Ivan Pavlov in his famous experiments with dogs. Just as Pavlov's dogs learned to salivate at the sound of a bell previously paired with food, patients can learn to produce physiological responses when presented with cues previously associated with effective treatment. If you've experienced relief from a particular medication multiple times, your brain learns to associate the act of taking that medication with the relief that follows. Eventually, even an inert substitute can trigger the learned response. This conditioning operates largely unconsciously, meaning you don't need to consciously believe in the placebo for it to work. The ritual of treatment itself, the familiar pill bottle, the act of swallowing, the doctor's reassurance, all these contextual factors can trigger conditioned healing responses. Different medical conditions show different patterns of placebo responsiveness. Pain is particularly sensitive to placebo effects, with studies showing that placebo treatments can provide relief comparable to active medications in some cases. Depression also shows substantial placebo effects, which complicates the testing of new antidepressant drugs. Parkinson's disease, as mentioned, demonstrates clear placebo responses in motor function. Even immune system functions can be influenced by placebos, with studies showing that expectation can affect inflammatory markers, cytokine production, and other immune measures. However, placebo effects have limits. They work best for symptoms mediated by the brain, things like pain perception, nausea, fatigue, mood, and motor function. They cannot shrink tumors, lower cholesterol, or cure infections. They modulate how you experience and respond to illness, but they don't directly attack disease processes that are independent of neural control. Understanding these boundaries helps clarify what placebo effects are and aren't capable of achieving. The nocebo effect represents the dark mirror of the placebo effect. While placebos produce benefit through positive expectations, nocebos produce harm through negative expectations. If you expect side effects from a medication, you're more likely to experience them, even if you're taking an inert substance. Clinical trials consistently show that patients in placebo groups report side effects, sometimes mirroring those reported by patients receiving active drugs. These nocebo effects are real, involving similar neural mechanisms as placebo effects, but activated by negative rather than positive expectations. The nocebo effect highlights an important ethical consideration. Telling patients that a treatment might cause side effects actually increases the likelihood of those side effects. Does informed consent become harmful? Medical ethics requires informing patients about potential risks, but doing so may trigger nocebo responses that wouldn't otherwise occur. This tension between transparency and therapeutic benefit remains unresolved, though most ethicists agree that honest communication remains paramount, despite potential nocebo effects. The social context of treatment strongly influences placebo effects. The quality of the doctor-patient relationship, the confidence conveyed by the healthcare provider, the appearance of the treatment setting, even the color and size of pills, all these factors affect how strongly placebo mechanisms engage. A doctor who expresses certainty about a treatment's effectiveness enhances placebo responses compared to one who seems uncertain or dismissive. This doesn't mean doctors should lie to patients or prescribe placebos deceptively. Rather, It suggests that the therapeutic relationship itself is a powerful component of healing, one that should be cultivated and valued alongside pharmacological treatments. Interestingly, placebo effects can occur even when patients know they're receiving placebos. This seems paradoxical. How can an inert treatment work if you know it's inert? Yet studies have demonstrated exactly this phenomenon, called open-label placebo treatment. Patients told they're receiving placebos, but that placebos can trigger beneficial healing responses, still show improvements in conditions like irritable bowel syndrome, migraines, and chronic pain. The explanation may involve several factors. First, the ritual of treatment itself, the daily act of taking a pill, visiting a doctor, participating in a healing process, can trigger conditioned responses learned from past medical experiences. Second, understanding the science of placebo effects may create positive expectations about the placebo's ability to help, effectively making the placebo work through informed belief rather than deception. Third, receiving any treatment, even a known placebo, conveys care and attention, which may have therapeutic value independent of the treatment's content. The existence of placebo effects raises profound questions about clinical trial design. To determine whether a new drug works, researchers compare it against a placebo. If the drug performs better than placebo, it's considered effective. But if placebo effects are themselves substantial, this sets a high bar for new treatments. Many drugs that seem helpful in clinical practice fail to outperform placebos in rigorous trials, not because they're useless, but because placebos are surprisingly effective. This has led to debates about how to interpret clinical trials and whether the placebo comparison is always the most meaningful benchmark. Some researchers argue that what matters is whether a treatment helps patients, regardless of whether it beats a placebo. If combining a drug's pharmacological effects with placebo effects produces better outcomes than either alone, why not embrace both? Others counter that we need to know which treatments work through specific mechanisms rather than general contextual effects, both for scientific understanding and for ensuring that expensive or potentially harmful treatments actually provide value beyond cheaper, safer placebos. The ethics of prescribing placebos deliberately remains controversial. If placebos can help patients, should doctors prescribe them? Traditional medical ethics says no, arguing that deceptive prescribing undermines trust in the medical profession and violates patient autonomy. Patients have a right to know what they're taking. However, the discovery that open-label placebos can work suggests a middle path. Doctors might prescribe placebos honestly, explaining that while the pills contain no active drug, they can trigger beneficial physiological responses through psychological mechanisms. This approach respects patient autonomy while harnessing placebo effects therapeutically. Some clinics have begun experimenting with this approach, particularly for chronic conditions where conventional treatments have limited effectiveness or significant side effects. Early results suggest that many patients appreciate the honesty and still benefit from the treatment. This represents a fascinating evolution in how we think about placebos, from nuisances that complicate research to potential therapeutic tools in their own right. The placebo effect also illuminates the mind-body connection more generally. For much of medical history, Western medicine treated the mind and body as separate domains. Physical illnesses were addressed with physical treatments, while psychological issues were handled separately, if at all. The placebo effect demonstrates conclusively that this separation is artificial. Your thoughts, beliefs, expectations, and emotions directly influence physiological processes. The brain is not separate from the body, but deeply integrated with it, constantly modulating immune function, pain perception, hormonal balance, and countless other systems. This integration means that psychological interventions can have physical effects, and physical treatments can have psychological consequences. It suggests that optimal healthcare should address both biological and psychological factors, recognizing that healing involves the whole person, not just the diseased organ or dysfunctional system. Mind-body practices like meditation, yoga, and cognitive behavioral therapy work partly through mechanisms similar to placebo effects, engaging expectation, conditioning, and neural modulation to influence health outcomes. As you settle into rest tonight, consider the extraordinary capabilities hidden within your own nervous system. Your brain contains pathways for reducing pain, modulating immune responses, influencing mood and energy, all waiting to be activated by the right combination of context, expectation, and ritual. You carry within you a pharmacy more sophisticated than any human creation, capable of dispensing precise doses of healing chemicals in response to need and belief. The placebo effect is not a weakness or a trick. It's a testament to the brain's adaptive power, to evolution's foresight in building systems that can harness psychological resources for physiological healing. Tonight, as your conscious mind releases its grip and you slip into sleep, these systems continue their quiet work, maintaining, repairing, optimizing. You need not understand them to benefit from them. They operate beneath awareness, ancient processes refined over millions of years, carrying you toward morning. A mysterious signal from space captured our attention for decades. On August 15, 1977, Jerry Eman, an astronomer volunteering with the Search for Extraterrestrial Intelligence project at Ohio State University, was reviewing computer printouts from the Big Ear radio telescope. The telescope had spent the night before systematically scanning the sky, recording radio emissions from space. Most of what it detected was cosmic noise, the random radio static that fills the universe. But on this particular page, Eman noticed something that made him grab a red pen. A sequence of 6 characters appeared in one column, representing an extraordinarily strong radio signal. The sequence read 6 E Q U J 5. This notation indicated signal intensity, with each character corresponding to a specific strength. The sequence showed the signal rising from background levels, reaching a peak, and falling back down over exactly 72 seconds, the duration the telescope could observe any given point as Earth's rotation carried it through the field of view. Eman circled the sequence and wrote one word in the margin: "Wow." The signal was remarkable for several reasons. It was extremely strong, about 30 times louder than the background noise. It was narrowband, concentrated in a very specific frequency, around 1420 MHz. This frequency corresponds to the emission line of neutral hydrogen, the most abundant element in the universe. In 1959, physicists had suggested that any civilization trying to communicate across interstellar distances would likely choose this frequency, precisely because hydrogen is universal. Any technological society would know about it. The signal's characteristics matched what SETI researchers had predicted for an artificial transmission from another civilization. The WOW signal originated from the direction of Sagittarius, near the constellation's western border. The telescope's design allowed it to determine the signal's location with reasonable precision, though not exact pinpoint accuracy. Researchers immediately wanted to find the signal again. If it was genuinely from an extraterrestrial civilization, expected it to either repeat periodically, if it was a beacon, or continue for an extended time, if it was a longer message or leakage from an alien civilization's own radio emissions. But when astronomers pointed telescopes back at the same region of sky, they found nothing. Subsequent observations over days, weeks, months, and eventually decades, never detected the signal again. This non-recurrence became one of the most frustrating aspects of the mystery. A genuine extraterrestrial transmission should be detectable more than once, either because the source continues transmitting or because it transmits regularly. The failure to detect it again suggested either that the transmission was extremely brief and directed, a single burst aimed at Earth that we happened to catch, or that it wasn't extraterrestrial at all, but some other phenomenon. Over the years, various explanations were proposed. Could it have been a satellite passing overhead? The signal's characteristics didn't match known satellites, and the telescope was designed to filter out obvious interference. Could it have been a secret military transmission? No evidence supported this, and the frequency was in a protected radio astronomy band where transmissions were forbidden. Could it have been a reflection or some instrumental artifact? Analysis suggested the signal was genuinely from space, not a local effect. One hypothesis that gained attention in 2016 suggested the signal came from a comet. 2 comets were in the general area of the sky when the signal was detected, and comets are known to produce radio emissions at the hydrogen frequency when they release hydrogen gas that gets excited by solar radiation. However, this explanation had problems. The signal was far stronger than typical cometary emissions, and follow-up observations of those comets didn't show similar signals. Most astronomers concluded that while a comet might produce weak hydrogen line emissions, it couldn't account for the WOW signal's intensity. In 2024, new research offered a more detailed natural explanation. Astronomers analyzing archival data from the now-defunct Arecibo Observatory in Puerto Rico found several weaker signals similar in character to the WOW signal. These signals were all associated with clouds of neutral hydrogen in interstellar space. Normally, these clouds produce faint radio emissions at the hydrogen frequency. But the researchers proposed that under certain rare circumstances, a powerful transient event, such as a flare from a magnetar, an extremely magnetic neutron star, could energize a hydrogen cloud, causing it to briefly emit intense radio waves in a process similar to a maser. A maser is like a laser, but from microwave radiation instead of visible light. It occurs when excited atoms or molecules emit coherent radiation all at the same frequency and phase. If a magnetar's radiation struck a hydrogen cloud at the right angle and with the right intensity, could stimulate the hydrogen atoms to emit a burst of coherent radiation at the hydrogen frequency. This burst would be intense, narrowband, and brief, matching the WOW signal's characteristics. The alignment required would be precise. The magnetar flare, the hydrogen cloud, and Earth would all need to line up correctly, making such events extremely rare. This rarity would explain why the signal was never detected again, and why similar signals are so uncommon. The explanation is still somewhat speculative. No one has directly observed a magnetar energizing a hydrogen cloud in this way, though the physics seems plausible based on what we know about masers and high-energy astrophysics. Some scientists remain skeptical, noting that the proposed mechanism requires very specific conditions that may not occur in nature as easily as the theory suggests. Others point out that even if this explanation is correct, it doesn't close the door on extraterrestrial intelligence entirely. It just means the WOW signal probably wasn't from aliens. The search continues, with modern SETI programs now using more sophisticated technology that can monitor millions of frequency channels simultaneously and respond to interesting signals in real time rather than discovering them days later in printed data. The WOW signal remains iconic in SETI history, representing both the hope and frustration of searching for cosmic companions. It showed that radio telescopes could potentially detect signals from other civilizations, if such signals exist. It demonstrated the challenges of distinguishing between natural astrophysical phenomena and artificial transmissions. And it illustrated the importance of confirmation. A single unrepeated signal, no matter how compelling, cannot definitively prove extraterrestrial intelligence. Science requires reproducibility. One measurement is a hint. Two measurements begin a pattern. But many measurements establish a fact. For decades, the wow signal stood alone, a tantalizing hint that refused to yield its secrets. Now it seems likely to join other, initially mysterious phenomena that eventually found natural explanations. The pulsars discovered in 1967 were briefly considered possible alien beacons before being identified as rapidly spinning neutron stars. Fast radio bursts, mysterious millisecond pulses detected in the 21st century, sparked speculation about extraterrestrial megastructures before being traced to various astrophysical sources. Again and again, the universe produces signals that seem artificial at first, but turn out to be natural, products of extreme physics, operating under conditions that stretch our understanding. This pattern doesn't mean extraterrestrial intelligence doesn't exist. The universe is vast, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Many of those stars orbited by planets. The raw numbers suggest life should have arisen elsewhere. The question is whether intelligent technological civilizations exist, whether they survive long enough to develop interstellar communication capabilities, whether they choose to transmit, and whether we're looking in the right places at the right times with the right equipment. The wow signal reminded us how difficult this search is. Even when everything seems right, when a signal matches predictions perfectly, when the excitement builds and the discovery seems within reach, nature can surprise us with phenomena we hadn't anticipated. The universe is more creative than we give it credit for, producing exotic astrophysical events that mimic the very signals we seek. As you prepare for sleep tonight, you might glance through your window at the stars beyond. Somewhere among those points of light, hydrogen clouds float in the darkness, occasionally illuminated by the violent flares of dying stars. Radio waves wash across space in all directions, carrying information about cosmic catastrophes, stellar births, and the endless churn of matter and energy. Our telescopes catch fragments of this radio symphony, most of it meaningless static, but occasionally something structured, patterned, purposeful seeming. We listen with hope and with rigor, knowing that even false alarms teach us something about the cosmos. The wow signal may not have been an alien greeting, but it expanded our understanding of what interstellar space can do, what natural processes can create. It reminded us that the universe doesn't need intelligence to produce order and pattern. Physics alone can generate complexity that rivals anything design might produce. And if the universe can fool us once, it can fool us again. So we listen carefully, check our work, and remain humble before the vast unknowing. Your gut contains a brain and influences your mood in mysterious ways. Inside your abdomen, wrapped around 20 feet of intestines, lies a network of approximately 100 million neurons. This is your enteric nervous system, sometimes called the second brain. It operates largely independently of your central nervous system, controlling digestion through its own neural circuits, releasing neurotransmitters, and communicating constantly with your brain through neural and chemical pathways. But this gut brain does more than manage digestion. It influences mood, emotion, cognition, and behavior in ways that scientists are only beginning to understand. The gut-brain axis, the bidirectional communication system between your gastrointestinal tract and your central nervous system, represents one of the most fascinating frontiers in neuroscience and medicine. The connection works both ways. Your brain can affect your gut, which is why stress often manifests as stomach problems. But your gut can also affect your brain, influencing everything from anxiety levels to decision-making. This might seem strange. Why would the organ system responsible for processing food have such profound effects on consciousness and mental state? The answer lies in evolution and in the intricate ecology of the trillions of microorganisms that inhabit your intestines. Your gut microbiome, the vast community of bacteria, archaea, fungi, and viruses living in your digestive tract, may contain more cells than your entire body has human cells. These microorganisms aren't just passive passengers. They actively interact with your body, producing vitamins, breaking down complex carbohydrates, training your immune system, and manufacturing neurotransmitters. Among the chemicals produced by gut bacteria are serotonin, dopamine, gamma-aminobutyric acid, and other molecules that significantly influence brain function. In fact, approximately 90% of your body's serotonin is produced in the gut, not the brain. While most of this gut-derived serotonin doesn't cross the blood-brain barrier to directly affect the brain, it influences the gut's own nervous system and communicates with the brain through other pathways. The vagus nerve, a major neural highway connecting your brain to your abdominal organs, carries signals in both directions. When your gut detects certain conditions, perhaps inflammation, specific nutrients, or chemicals produced by gut bacteria, it sends signals up the vagus nerve to your brain. These signals can influence mood, stress responses, and even social behavior. Animal studies have shown that cutting the vagus nerve disrupts many of the effects gut microbes have on the brain, confirming the importance of this neural connection. But the communication doesn't rely solely on neural pathways. Gut bacteria produce metabolites, chemical compounds that enter your bloodstream and can affect distant organs, including the brain. Some of these metabolites influence inflammation, which has been linked to depression and other mood disorders. Others affect the permeability of the blood-brain barrier, potentially allowing molecules to enter the brain that would normally be excluded. Still others interact with immune cells, which themselves can influence brain function. Research over the past 2 decades has revealed startling connections between gut health and mental health. Studies in mice have shown that altering the gut microbiome through antibiotics, probiotics, or fecal transplants can change behavior, affect anxiety levels, and influence social interactions. Mice raised without any gut bacteria, called germ-free mice, show abnormal brain development and behavior compared to normal mice. When these germ-free mice receive gut bacteria from mice with anxiety, they become more anxious. When they receive bacteria from calm mice, they become calmer. This suggests that gut bacteria don't just correlate with behavior, but can actually cause behavioral changes. Human studies are more limited, but increasingly suggestive. People with irritable bowel syndrome, inflammatory bowel disease, and other gastrointestinal disorders have higher rates of depression and anxiety than the general population. This could simply mean that having a chronic illness is depressing, which is certainly true. But evidence suggests a more direct link. The composition of gut bacteria differs between people with depression and healthy controls. Some studies have found that probiotic supplements containing specific bacterial strains can improve mood and reduce anxiety, though results have been mixed and many questions remain about which bacteria help, at what doses, and for which people. The gut microbiome influences not only mood, but also cognition. Some research suggests connections between gut health and conditions like autism, Alzheimer's disease, and Parkinson's disease. In Parkinson's disease, abnormal protein aggregates appear in the gut years before motor symptoms develop, leading some researchers to hypothesize that the disease might actually begin in the gut and spread to the brain via the vagus nerve. While this remains controversial, it highlights how intertwined gut and brain really are. Diet plays a crucial role in shaping the gut microbiome. What you eat determines which bacterial species thrive and which decline. A diet high in processed foods and sugar promotes different bacteria than a diet rich in fiber, fruits, and vegetables. These dietary effects on gut bacteria may partially explain how nutrition affects mental health. Some researchers have begun investigating whether dietary interventions could be used to treat depression and other mood disorders, not just through the direct effects of nutrients on the brain, but through their effects on gut bacteria that in turn influence the brain. The implications extend beyond individual health to our understanding of self. If your mood and behavior are influenced by trillions of microorganisms living inside you, are they part of you or separate entities? In one sense, gut bacteria are clearly separate organisms with their own genes and evolutionary interests. But in another sense, they're so integrated into your physiology, so essential to your normal functioning, that it makes sense to think of yourself as a superorganism, a cooperative community of human cells and microbial cells working together. This perspective challenges simplistic notions of biological individuality. The gut-brain axis also raises questions about free will and personal identity. If gut bacteria influence your mood, cravings, and decisions, are your choices entirely your own? The question becomes even more complex when you consider that your gut microbiome changes constantly, influenced by diet, medications, stress, and environmental factors. Are you the same person when your gut bacteria are different? These questions may seem overly philosophical, but they have practical implications for how we think about mental health and treatment. If depression has a microbial component, treating it might require addressing gut health, not just prescribing antidepressants that target brain chemistry directly. One of the most intriguing aspects of gut-brain research involves how social behavior might be influenced by gut microbes. Some bacteria produce compounds that encourage their host to seek out other individuals, potentially spreading the bacteria to new hosts. In mice, gut bacteria have been shown to influence social behaviors like grooming and aggression. Whether similar effects occur in humans remains uncertain, but the possibility is fascinating. Could your desire to be around others or your preference for solitude be partially influenced by your gut microbiome? Could personality traits have microbial components? These questions are still far from answered, but research is moving in directions that may eventually provide insights. The gut also houses much of your immune system. Approximately 70% of immune cells reside in gut-associated lymphoid tissue, where they interact constantly with gut bacteria. This interaction educates the immune system, teaching it to distinguish between harmless bacteria and dangerous pathogens. Disruptions in this process can lead to autoimmune diseases, allergies, and chronic inflammation, all of which can affect the brain. Depression, for instance, is associated with elevated inflammatory markers, suggesting that immune dysregulation might contribute to mood disorders. If gut bacteria influence immune function, and immune function influences mood, then gut bacteria may affect mood partly through immunological mechanisms. The complexity of these interactions makes studying the gut-brain axis challenging. Cause and effect become difficult to disentangle. Does depression change gut bacteria, Or do gut bacteria cause depression? Probably both are true to some degree. The relationship is bidirectional and dynamic, with changes in one system affecting the other in feedback loops that can either maintain health or spiral toward disease. Understanding these dynamics could lead to new treatments. Researchers are exploring whether specific probiotics, prebiotics, dietary interventions, or even fecal transplants might help treat mental health conditions. Early results are promising in some areas, though the field is still young. And many claimed benefits of probiotics are not yet well supported by rigorous research. The gut microbiome is also remarkably personal. No two people have identical microbial communities. Your gut bacteria are influenced by your genes, but even more so by your environment, diet, lifestyle, and experiences. Infants acquire their initial microbiomes during birth and breastfeeding, setting the stage for lifelong patterns. Antibiotics can dramatically alter the microbiome, sometimes permanently. Travel, illness, aging, all these shape the microbial ecosystem within you. As you rest tonight, trillions of bacteria are working inside you, breaking down the remnants of your last meal, producing vitamins and neurotransmitters, communicating with your immune cells and nervous system. They're not invaders but partners, co-evolved with humans over millions of years to form a mutually beneficial relationship. You feed them, they help you digest, defend against pathogens, and apparently influence your thoughts and feelings in ways we're still discovering. This partnership operates entirely below consciousness. You don't feel the bacteria working, don't sense their chemical signals traveling up the vagus nerve. But the effects are real, shaping mood, health, and perhaps even aspects of personality. The boundary between self and other becomes fuzzy at this microscopic scale. You are not just your neurons and genes, but also the trillions of microbes that call you home. The mystery deepens when you consider that science has only scratched the surface. Most gut bacteria cannot be cultured in laboratories, meaning we know they exist through genetic sequencing, but understand little about what they do. The interactions between different bacterial species, between bacteria and human cells, and between the gut and brain involve thousands of variables operating simultaneously. Unraveling this complexity will take decades of research. For now, the gut-brain axis remains partially mysterious, a frontier where neuroscience meets microbiology, where ancient evolutionary partnerships shape modern minds, where what you eat for breakfast might influence how you feel by afternoon through pathways still being mapped. It's a reminder that your body is not a machine with separate parts, but an ecosystem, a community of life forms working together, producing the unified experience you call consciousness. Sleep well, knowing that even as you rest, your inner universe continues its work, maintaining the intricate balance between brain and gut, between self and symbiont, between the 1,000,000,001 parts that together make you whole. Certain numbers appear throughout nature with mysterious frequency. If you examine the spirals in a sunflower's center, count the arrangement of pinecone scales, measure the proportions of nautilus shells, or analyze the branching patterns of trees, you'll encounter the same sequence of numbers appearing again and again. These are the Fibonacci numbers: 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on, each number the sum of the two preceding ones. Even more mysteriously, the ratio between successive Fibonacci numbers approaches a special value called phi, approximately 1.618, known as the golden ratio. This number appears not only in nature, but in art, architecture, and human aesthetic preferences in ways that remain only partly understood. The Fibonacci sequence itself is easy to describe. Start with 1 and 1. Add them to get 2. Add 2 and 1 to get 3. Add 3 and 2 to get 5. Continue this pattern forever, and you generate the Fibonacci sequence. The sequence was described by Italian mathematician Leonardo Fibonacci in 1202, though it was known to Indian mathematicians centuries earlier. What makes it remarkable is not the mathematical definition, which is simple, but the ubiquity of these numbers in natural forms. Flower petals commonly come in Fibonacci numbers. Lilies have 3 petals, buttercups have 5, delphiniums have 8, marigolds have 13, asters have 21, and daisies often have 34, 55, or 89. Not every flower follows this pattern, and there's variation within species, but the tendency toward Fibonacci numbers is striking. Why would plants favor these particular numbers? The answer relates to how plants grow and pack structures efficiently. The seeds in a sunflower head, for instance, are arranged in spirals that curve both clockwise and counterclockwise from the center. If you count the number of spirals in each direction, you'll typically find 2 consecutive Fibonacci numbers, perhaps 34 spirals in one direction and 55 in the other. This arrangement isn't random. It emerges from the way new seeds are added at the center and pushed outward as the flower grows. Each new seed appears at an angle relative to the previous one, and the optimal angle for packing seeds efficiently turns out to be related to the golden ratio. Specifically, the golden angle, which is approximately 137.5 degrees, represents the fraction of a full circle equal to the golden ratio. When seeds are positioned at this angle relative to each other, they pack together with minimal wasted space and no large gaps. This packing efficiency maximizes the number of seeds a sunflower can produce, providing an evolutionary advantage. Plants whose genetic programs happened to position seeds at angles close to the golden ratio produced more offspring, and natural selection favored this trait. Similar principles apply to leaf arrangement on stems, called phyllotaxis. Leaves are typically positioned at specific angles around the stem, such that they don't directly shade each other, maximizing sun exposure. The optimal angles for this arrangement also involve the golden ratio and Fibonacci numbers, again, because these mathematical relationships emerge from efficient packing under spiral growth patterns. Pine cones and pineapples show analogous Fibonacci spirals in their scale arrangements, resulting from similar growth processes. The nautilus shell presents a different manifestation of the golden ratio. As the nautilus grows, it adds chambers to its shell in a logarithmic spiral, each chamber larger than the previous one by a constant ratio. While there's debate about whether actual nautilus shells precisely follow the golden ratio, the shell's growth pattern does approximate a logarithmic spiral, and such spirals can be related to the golden ratio when the expansion factor takes certain values. The visual similarity between nautilus shells and the golden spiral has made the nautilus an icon of mathematical beauty in nature, though the precise relationship is less exact than popular accounts sometimes suggest. The human body also shows some Fibonacci-related proportions, though again with less precision than popular mythology claims. The ratio of arm length to forearm length, the proportions of fingers, and various facial measurements approximate the golden ratio in some individuals, but show considerable variation. The aesthetic appeal of golden ratio proportions in human faces and bodies has been debated for centuries. Some studies suggest that faces with proportions closer to the golden ratio are perceived as more attractive, but other studies have failed to replicate these findings. The evidence suggests that while the golden ratio may play some role in aesthetic preferences, it's far from the only factor determining attractiveness. In art and architecture, the golden ratio has been used deliberately by creators who believed it produced especially pleasing proportions. The Parthenon in Athens is often cited as incorporating golden ratio dimensions, though measurements of the actual structure don't perfectly match the ideal ratios. Renaissance artists like Leonardo da Vinci studied mathematical proportions and may have used the golden ratio in some works, though definitive evidence is limited. The 19th century Swiss architect Le Corbusier explicitly incorporated the golden ratio into his designs, creating a measurement system called the modulor, based on human proportions and the golden ratio. Whether these deliberate uses of the golden ratio actually improve aesthetic quality is subjective and debated. Music, too, has been analyzed for Fibonacci numbers and golden ratios. Some composers, most notably Béla Bartók and Olivier Messiaen, deliberately incorporated these mathematical relationships into their compositions, using Fibonacci numbers to determine the lengths of sections or the placement of climactic moments. Whether listeners can perceive these structures unconsciously and whether they enhance musical beauty remains uncertain. The appeal of Fibonacci numbers and the golden ratio partly comes from their mysterious ubiquity. How can the same simple mathematical pattern appear in sunflowers, galaxies, and human faces? One answer is that these patterns emerge naturally from certain types of growth and optimization processes. When things grow proportionally, adding new elements in ways that maintain geometric relationships with existing elements, Fibonacci-like patterns often result. It's not that nature consciously chooses these numbers, but that the physical and biological processes that shape natural forms tend towards certain mathematical attractors. Another explanation is confirmation bias. We notice Fibonacci numbers when they appear and overlook the many cases where they don't. The human mind is excellent at pattern recognition, sometimes seeing patterns even where none exist. This doesn't mean Fibonacci patterns in nature are illusory, but it does mean should be cautious about overstating their prevalence or significance. Not every spiral in nature follows the golden ratio. Not every branching pattern involves Fibonacci numbers. Nature is more diverse and less mathematically pure than simplified accounts suggest. Nevertheless, the genuine examples are remarkable enough. The fact that simple mathematical rules, describable in a few words, can generate the complexity we see in sunflowers, pine cones, and galaxies is profound. It suggests that beneath the surface diversity of natural forms lies a deeper unity, that the universe operates according to mathematical principles we're only beginning to understand. Mathematics isn't just a human invention for describing nature, but is somehow embedded in nature's fabric, woven into the laws that govern how matter and energy organize themselves. Some physicists and philosophers have argued that the universe is fundamentally mathematical, that physical reality is in some sense identical to mathematical structure. This view, sometimes called mathematical Platonism, holds that mathematical objects like numbers and geometric forms have an existence independent of human minds, and that the physical world instantiates these forms. The prevalence of specific mathematical patterns in nature lends support to this perspective, though it remains deeply controversial. As you settle into rest tonight, you might reflect on the patterns surrounding you. The branching of blood vessels in your body, the rhythm of your heartbeat, the structure of your lungs, all show fractal and Fibonacci-like characteristics. Your body, like a sunflower or a nautilus, grew according to rules that generated mathematical patterns. You are a walking embodiment of geometric principles, a biological expression of numerical relationships, a conscious manifestation of the same mathematics that organizes galaxies and guides the spirals of seashells. The universe appears to operate according to deep mathematical order, from the quantum scale, where particle interactions follow precise equations, through the middle scale of everyday objects, where Fibonacci spirals bloom in gardens, to the cosmic scale, where galaxies wheel through space in patterns that seem to echo golden spirals. This mathematical harmony might be coincidence, or it might reveal something fundamental about reality itself. We don't yet know. For now, it remains a mystery, beautiful and tantalizingly close to comprehension, like a pattern half glimpsed in shadows, suggesting order and meaning just beyond our grasp. The Belém Tower in Lisbon, the paintings of Salvador Dali, the music of Debussy, the structure of DNA, the proportions of credit cards. All these and countless other human creations have been analyzed for golden ratio content, sometimes with genuine correlations, often with spurious pattern matching. We are drawn to this number, 1.618, as moths to flame, seeking in its elegant simplicity some key, beauty and truth. Perhaps we find what we seek because we carry the pattern within us, encoded in the helical stairways of our genes, expressed in the proportions of our limbs, reflected in the neural architecture that allows us to recognize and appreciate these same patterns when we encounter them in art or nature. Or perhaps we overestimate our own mathematical perfection, projecting order onto chaos, seeing Fibonacci numbers where only roughly similar values exist. The truth, as usual, lies somewhere between extreme positions. The patterns are real, but not universal. The mathematics is embedded in nature, but not with perfect precision. And our appreciation of these patterns mixes genuine aesthetic response with learned cultural associations and cognitive biases that favor pattern detection even when patterns are weak or coincidental. What matters is not whether every claim about Fibonacci numbers proves true under scrutiny, but that enough genuine examples exist to pose the question: why does mathematics work so well at describing the world? This question, articulated by physicist Eugene Wigner as the unreasonable effectiveness of mathematics, remains one of the deepest in science and philosophy. We might have expected the universe to be chaotic, arbitrary, governed by no consistent laws. Instead, we find that a few mathematical principles allow us to predict eclipses centuries in advance, to design machines that carry us to the moon, to understand the fundamental forces that shape reality. The prevalence of Fibonacci numbers in nature is one small part of this larger mystery, a thread that, if pulled, might unravel our understanding of what mathematics is and why it permeates the physical world so thoroughly. For tonight, let these patterns be a comfort. You live in a universe that, for all its apparent chaos and randomness, contains deep order. The mathematics that spirals seeds in sunflowers also governs the atoms in your body and the stars in distant galaxies. You are part of this mathematical tapestry, a conscious thread woven into a pattern that extends beyond human knowing. As you spiral down towards sleep, tracing your own golden path from wakefulness into dreams, you recapitulate in miniature the same principles that organize nature from the smallest scales to the largest. The universe is mathematical, and so are you. You have done enough for today. Let your thoughts slow and scatter like leaves settling after wind. The mysteries we've explored tonight, dark matter holding galaxies together, consciousness emerging from neurons, signals from space that may or may not speak of other minds, the invisible bacteria shaping your moods, the mathematical patterns hidden in shells and flowers, All these remain partially unexplained, and that is perfectly fine. Not everything needs to be understood tonight. Not every question requires an answer before you rest. The universe has kept its secrets for billions of years. They will wait through one more night while you sleep. Close your eyes now. Feel the weight of your body against the bed, the gentle rhythm of breath moving in and out. Your consciousness, that mysterious light that has accompanied you through this journey, will soon dim and transform into something else entirely, into the strange landscapes of dreams where the rules change and the impossible becomes ordinary. You need not understand how this transformation happens. You need not solve the hard problem of consciousness or map the neural correlates of subjective experience. Simply allow it to occur as it has every night of your life, as reliable as sunrise, as natural as the Fibonacci spirals in flowers. Tomorrow, the questions will still be there. Scientists will continue their patient work, gathering data, proposing theories, testing hypotheses against the intricate reality of what is. Dark matter will continue holding galaxies in its invisible embrace. Ball lightning will perhaps flicker somewhere in a thunderstorm, witnessed by someone who will wonder what they saw. The Tao's hum will hum on for those who hear it. The gut microbiome will keep shaping moods and minds. And the golden ratio will keep appearing in sunflowers, nautilus shells, and the proportions of growing things. But tonight, none of this is your concern. Tonight, you are permitted to not know, to not solve, to not understand. Tonight, you can rest in the comfort of mystery, in the knowledge that the universe is far stranger and more wonderful than any explanation could capture. You are a small part of this vast, inexplicable cosmos, a temporary gathering of atoms into consciousness, and that consciousness now deserves rest. So let the unexplained remain unexplained. Let the mysteries be mysterious. Let your mind release its grip on questions and sink into the soft darkness of sleep. You are safe. You are whole. You have traveled through wonders tonight, and now you return to the simplest wonder of all, the daily dissolution of waking awareness into sleep, that small rehearsal for the larger mystery that awaits us all. Dream well, traveler. Dream of spirals and signals, of particles and patterns, of all the beautiful strangeness that fills this cosmos we briefly inhabit. And in the morning, wake gently to find the world still here, still mysterious, still waiting to reveal one more secret, and then another, in the endless unfolding of understanding that defines the human journey. Good night.